Why hello lovely humans, Jen Foxbot here, and welcome back to another super awesome edition of Math Mondays! Oh yeah! Alright, I'm so glad that you're here and that we're going to do some math together today. The last episode was on the Heisenberg uncertainty principle, and that got me thinking, we could talk about the Schroedinger Wave Equation! Yes! But wait, talking about that equation and really understanding what it means requires a little bit of knowledge about waves and how we use mathematics to represent waves. So instead of diving right into the Schroedinger Wave Equation, I thought it would be super helpful to talk about classical wave theory and how we use equations to represent waves. So here we go. So the first thing that physicists and a lot of mathematicians like to do to understand a particular problem is to draw a picture. So I'm going to draw my little wave over here. And the first thing that we have to do when we draw an axis is label it. So we're going to call this axis Y and the horizontal axis X. So basically what that tells you is our wave is going to be a snapshot. Okay, so basically, if you were sitting on a surfboard out in the middle of the ocean and you saw a bunch of waves going past you, then your horizontal axis would be in time. But if you're sitting there and you took a picture of the wave, this is what your camera might show if you drew an axis on top of it. So the height of our wave is called the amplitude. And the distance between two crests, or two troughs of the wave, is the wavelength. And the frequency is the time that it takes a point on the wave to travel one full cycle. So basically a point on the wave to get back to where it started from. So if this was a graph of our wave over time, this length in time would be the frequency. Can't quite label it on this picture since this is distance or space, but I think you get the picture. And then we have that super famous and handy-dandy equation that the velocity of our wave, or point on the wave, equals the wavelength times the frequency. That's an F. Okay, so V equals lambda F, wavelength times frequency. Okay, so now what? What do we do? How do we create an equation that represents this wave? Well, fortunately, there have been a lot of mathematicians to come before us so we can stand on their shoulders and save some time. And what we will find is that all waves must obey the classical wave equation, which looks like this. The second partial derivative with respect to x, equals 1 over the velocity squared times the second partial with respect to time. Okay. Oh, you're like, what the heck is that? Well, never fear. This equation basically just tells us what a function of y must look like. So the first thing that I can tell you from this equation is that our wave repeats over space and over time, which makes sense because waves propagate through space and time and they repeat, right? That's like basically the fundamental thing about waves is that they repeat over time. And so that helps us to guess a particular solution. And since I've done this before, I'm going to guess something that I know will solve this. Honestly, that's what a lot of higher level calculus is about, is understanding what these mean and what particular solutions look like. And what do I mean by a solution? Well, basically, I'm looking for an equation for y that depends on space, x, and time, t. And I'm looking, that solution, that equation for y, must meet this criteria. So whatever function I propose, let's say I propose x squared, if I were to take the second differential with respect to x and the second differential with respect to t, it must obey this equation. So do you think this solves that? if I take the second differential with respect to t, what do I get? Nothing. Oh, phoo. So in this case, dy dt squared equals 0. But dt equals 0. dy dx equals 2x. And d squared y dx squared equals 2. So 0 does not equal 1 over v squared times 2. So this does not solve our wave equation. What we are looking for, an equation that will solve this relationship, is something that repeats over time. Cool. So we can use the trigonometric functions for that. Heck yeah. What do I mean by that? Basically sine and cosine. And so I'm going to propose that our solution looks something like this. Y, as a function of space and time, equals a naught is just a constant, times sine k, a constant, times x, minus omega, another constant, times t. So here are my two variables. Now what I have to do is I have to take the second partial derivative with respect to x, second partial derivative with respect to t, set them equal to each other with this factor of 1 over v squared, and check that my solution comes out right. So let's do that. Yeah! Okay, so dy dx, so the derivative of y with respect to x, treat t like a constant, and so you get a naught, derivative of sine is cosine of kx minus omega t times a factor of k. And I take the second derivative, dy dx squared equals, we're going to get another, well, whatever, that's fine. So a naught, derivative of cosine is negative sine. So we get negative sine, sine kx minus omega t, and we get another factor of k to go with our first one. So if I make some more space here, we get a negative a naught k squared. I move that k to the front, we get another one. Cool, so that's dy dx squared. And then, sorry, my handwriting's slopey. And then over here, we're going to take the second differential with respect to time. So dy dt equals a naught cosine kx, treat x like a constant, and t is now our variable, minus omega t, so we get a factor of negative omega. And then we're just going to rewrite this, negative a naught omega cosine kx minus omega t. Okay, so that's the first partial derivative. The second, d squared y dt squared equals, derivative of cosine is negative sine. So our negative turns into a plus. We get a naught omega times sine kx minus omega t. We get another factor of negative omega. Okay, so now we set these two equal to each other. So we have a naught k squared times sine kx minus omega t equals 1 over v squared. This is a long equation. 1 over v squared times d squared y dt squared, which is negative a naught omega squared sine kx minus omega t. Okay, cool. Yeah! So here is our solution put into the classical wave equation. So, first thing that we notice, oops, I forgot a negative. Haha, that's a good thing. Okay, it's a good thing that the negative's there. Okay, so first thing that we want to do is cancel anything that we see is the same on both sides, because basically what we would do is we would just divide both sides by that thing. So for example, divide by negative a naught, and all of a sudden our negative a naughts go away. Then we also see that the sign is the same on the both sides, which is good, so we can cancel those, and we're left with k squared equals omega squared over v squared. And then we can solve for v, and we get v squared equals omega squared over k squared. And that was my attempt at an arrow. Okay. And then we get V equals omega over K. Huh. Interesting. So at the beginning, we just said that omega and K were constants. We didn't define them. And now we're getting something that looks like surprisingly similar to this relationship. We just have to manipulate omega and K a little bit. And here's the trick. Omega is related to the frequency. Well, you could figure that out too, because omega is the constant in front of time. So it has to affect the time of our wave somehow. And K is the constant in front of X. So that has to do with the wavelength. And now you're like, okay. And if you were to look it up, you would find that omega is actually defined as the angular frequency. So omega is 2 pi f. And here, okay, we're going to write this here to make it a little bit easier for me. Okay, so V equals omega, V equals, I don't know, my chalk's being all funky, omega over K. Omega is 2 pi f, and K is called the wave number, and K equals 2 pi over the wavelength. Huzzah! So if we plug these two in, we get V equals the wavelength times the frequency. Yes! Our solution solved the wave equation. So that means that this equation is a valid solution to the wave equation, and that this represents a real wave. So then, once we have proven that our proposed solution is an actual solution, then we can start to define those constants. So what you would find if you had a particular wave that you took a snapshot of and you were trying to match it to this equation, you would need to match the amplitude, you would need to match the amplitude of your wave to the constant in front of your equation, because that's going to grow and shrink your wave. If you have A naught is 10, then the height up here is going to be 10, and the height down here is going to be negative 10. If you have a fraction, like 1/2, then these are going to change accordingly. That part's pretty straightforward, which is handy. Then K, the number that you put in for K, is going to change the wavelength of your wave. So if you make K a smaller number, your wavelength's going to shrink. And if you make K a bigger number, your wavelength's going to increase. Similarly for omega, omega affects the frequency of your wave. So if you increase the frequency, your wave is going to go, wah! Super fast. And if you, this is hard to see. If you increase the frequency, it'll propagate faster. And if you decrease the frequency, it'll be much, much slower. So there you have it. Here is a solution to the wave equation. And you can adjust the different constants to get a particular repeating wave. There are many, many solutions. I'm going to erase this. There are many solutions to this wave equation. And this particular second order differential equation, it's second order because it's the second derivative. It's differential because we're talking about derivatives and not integrals. So this second order differential equation is linear, meaning that any solution can also be, any two solutions can be added together to form another solution. So that basically means that if I have another solution, y2 of x and t equals some function of x and t that I know solves this, then you can say a third solution equals our first solution, a naught sine kx t plus f of x and t. That's pretty cool. That basically is called superposition. And that's where I'm going to leave it. I'm going to give you some homework because I think it's super useful to go through the motions yourself. So what would happen if you switched sine to cosine? Does that still solve the wave equation? So I want you to repeat what I did. You can use the exact same form, but just change sine to cosine. So it would be cosine of kx minus omega t. Run through the two partial derivatives, set them equal to each other, and see what you get. Alright, so thank you very much for watching. If you have any questions about anything that I mentioned in this video, please leave it in the comments. And if you have any particular mathematics topics you would like me to cover, also let me know, because this is for y'all. Yes. So I think the next video I'll talk about wave packets, and then after that we can dive into the Schroedinger wave equation. Alright, thanks very much everybody, and have a great rest of your day. Bye!